All right. So inertia is the key word today. And I think you guys can finish some of these sentences for me. Let's see. An object at rest will stay at rest. An object in motion will stay in motion. You guys do that already. Unless acted on by an unbalanced force. Okay? So an object at rest, it will just stay at rest forever unless an unbalanced force is in play. And an object in motion will stay in motion forever unless there's an unbalanced force. In other words, objects are kind of lazy, and they will just keep doing exactly what they're doing unless an unbalanced force makes them do something different. Okay? So if you put something on a shelf and it's at rest, it will literally stay on that shelf forever until an unbalanced force makes it do something different. Hey, Dom, you got to give her those headphones here, bud. Okay. Thank you. Anyways, now this idea that objects want to keep doing what they're doing, that's known as their inertia. And that is the term today. Inertia, inertia, inertia. Hey, this has happened a few times throughout the year where it's like, hey, just put the headphones on your table or something. It'll be fine. All right. In like Unit 3. Oh, I want a perfect on a test? Okay, well, at some point you're going to have to drop terms like conductor and insulator. Otherwise, that's just not happening. Okay? Or like, oh, I want a perfect on a test in like Unit 2. Well, you're going to have to talk to me about the word density. If you don't drop that term, then that's never going to happen. Okay? And the same way, if you want perfect on your Unit 8 test over forces, you're going to have to drop that word inertia and make sure you show me that, hey, I know what that means. All right? Hey, son, just make sure they're off the ears, that's all. Just make sure they're off the ears, yep. All right, so anyways, we refer to this as Newton's first law. He has 3 laws. So notes 3 is about the first law, notes 2 is about the second law, or notes 4 is about the second law, and notes 5 is about the third law. But we often just call this his law of inertia. So the first law of inertia, they're the same thing. Okay? So I'm going to try a series of demos here. I will do a few myself to start, and then you guys will start to get to do some stuff, which is fun. So this first one is about books on a rolling chair. Okay? So what I'm going to do is I'm going to put these books in motion. Okay? And I'm going to make sure when I slide this chair, it's going to hit that little island up front. So the books will be put in motion, and let's see what happens once the chair stops and it hits the front thing. What do the books do?
Why'd they fly?
They fly off, right? Okay? So let's think about why that was. The books were in motion. Okay? So what do the books want to keep doing? They want to stay in motion.
But they stopped.
They didn't know the books flew off, right?
But they stopped after.
Eventually, because they hit the floor. But the books were in motion. You come on in, Miss Bay. So what did they do? They stayed in motion because of their what?
Inertia.
Because of their inertia. Okay, I'm going to try another demo here in a second with Miss Bay.
Yeah, but I'm going to beat him. I'm too better.
You're too better?
I'm going to do it better.
Did you learn how to speak English too good?
I did it better. I'm doing it better.
She's not very good at it. We'll try. All right, so Miss Bay failed terribly, but I nailed it. The marker was what? The marker was at rest. And what did the marker want to keep doing? It wanted to stay at rest because of its what? Of its inertia. All right. This one's called the infinity beads. Maybe you've seen this one or a version of this before. Uh-oh. I dropped the ends of my beads in there. Come here. Where's the ends? Oh, there we go. All right, so what I'm going to do is I'm going to put these beads in motion.
You know what happens? It looks like it's flying.
And let's see what happens. I'm going to put them in motion and... What are they doing? In motion. Because of what? Color change. They're going to stay in
Do
motion.
you have to keep breaking it every period?
I didn't mean to that time or last period. Well, last period someone stepped on it, but the beads were in motion. And what they do, they want to
Stay in motion.
stay in motion because of their inertia. Uh-huh.
You'll give me a line sharpener. You'll go like shit. Bitch. I'm sorry.
Easy. Inertia. All right, and lastly, now this one, it looks like what I want to happen is to look like it's a fail, but we'll see. I've got a water bottle that's full. I got a water bottle that's empty, and I want to pull this just right so that I get a different result. Let's see here. If I do it just right. Yes. Do you see how the water bottle with water stayed up?
Has more mass.
Yeah, so here's the idea. The water bottle, the full bottle, was at rest, let's say, quiet please, quiet please, quiet. The bottle that was full was at rest, let's say, better than the empty bottle. So what's the deal with that? So you guys see how that bottle stayed at rest better? So let's talk about that. With this last demo involving water bottles, we saw that an object's mass affects its overall inertia. Objects with more mass have more weight and therefore more inertia. Or you'll hear me say a lot, big mass, big inertia. Big mass, big inertia. How you No. We're in the middle of notes and do stuff. Okay? Plus you're about to miss some cool demos. Alright, big mass, big inertia. Objects with less mass have less weight, and therefore less inertia. Little mass, little inertia. Big mass, big inertia. Little mass, little inertia. Yes, I'm not going to let anyone go for a while. Big mass, big inertia. You're going to want to use that kind of phrasing come test time, I think. Now, the weight of an object can be described using the following equation. Weight, or W, equals m times g. W equals m times g. Alright. The W stands for weight in newtons. Of course, there's capital N that you can use for newtons. What do you guys think M stands for?
Mass.
Mass, and that will be in kilograms. Now, we already have mass, because that's the M. What do you guys think the G is?
Grams.
Grams, that's a mass though. So it's not that. We already have mass with M.
Gravity.
Gravity. It's the acceleration due to gravity. And that'll be in meters per second squared, baby. Remember that unit from Unit 7?
Wait, stop. You went too fast. Way too fast.
Getting a cramp in your paw?
Yeah.
Okay. So W equals M times G. Or put differently, the weight of something will be equal to its mass times its gravity. Don't have music playing, do you, Dom?
I don't have my
Okay.
head is long. Wait.
Anyways, now an object's weight, it does depend on, come on, eraser, the gravity it experiences. So, like, if you mess with this G right here, W is going to change. So that G gets bigger or smaller, the W will change. Okay?
5 or S.
S squared, second squared, yeah, meters per second squared. So an object's weight depends on the gravity experiences, but the object's mass doesn't change no matter where it is. So mass is a measurement of how much stuff you have. So the amount of stuff doesn't change no matter what the gravity is. So for example, I want to be really clear about this. A 1 kilogram rock on Earth has a mass of 1 kilogram on the moon. The mass of something on Earth and the moon is going to always be the same. Okay?
What's the one that it changes on the planet?
The same rock has a weight of 9.8 newtons here, with a weight of 1.6 newtons on the moon. So your weight is totally different on the moon, even though you're still made up of the same amount of stuff. Okay? So how hard you're being pulled down is different. Okay? How hard you're pushing down, being pulled down is going to be different. Your weight will be different. Because the gravity is different, but the mass will not change no matter what plane you're on. Okay, so I'm going to pause for a minute here, and we're going to try a series of demos ourselves. Okay, So I hope you guys enjoyed those demos there. They're all having to do with inertia, like the penny falls in the cup because the penny's at rest, stays at rest, it's inertia. All that good stuff. Now this worksheet, the top half, those are good like practice test questions. So we're going to go through those here. And then the bottom half, those are good practice quiz questions. Okay? So let's do the first practice test question again. I'll give you guys a couple minutes. You are riding in a car and the driver slams on the brakes. What happens to you and why? Yes?
You go forward,
You fly forward. Absolutely.
and then you go.
And why is that? Think about terms that we've used today.
Because you stay in motion.
Yeah, you're in motion, so you stay in motion because
Of inertia.
of your inertia, right? So that'd be a great response. You were in motion. So what did you do? You stayed in motion. And why did you do that? Because of your inertia. Okay? If that were a test question, I would absolutely have to see terms like motion, and I would absolutely have to see the word inertia. There's no way you're getting full credit if you don't give me that word. No way. No way. That's why we're practicing now. I want you guys to get used to this, right? So there's no way you're getting full credit without the word inertia. All right, why don't you guys try 2, 3, and 4, and we'll touch base here in a minute. Okay, try 2, 3, and 4.
I already did that.
All right. Hey, when the driver takes a really hard turn, what do?
You lean to the side.
You lean to the side, you kind of hit the window or something. You slide across your seat, something like that. But you slide to the side of the car somehow. You
Slam against the floor.
Yeah, whatever it is. Why?
Because you're staying in motion with the car.
So the car turned left. Which way were you going before the car turned? Straight, forward, whatever. So what does your body want to keep doing?
No, your body wants to stay in the direction the car's going.
Yeah, your body wants to keep going forward. So if the car then turns left, your body's just going to keep going forward and you hit the right side of the car. Does that kind of make sense? So your inertia was forward, so you kept moving that way. And that's why, and just the thing is, the car turned, so then all of a sudden, going forward means you hit the side of the car. But you're still going in the same direction. Okay? Hey, so you left your pencil on top of your homework. Your teacher comes by, quickly snatches the homework, like, give me that! Okay? Your pencil doesn't move at all. Why didn't the pencil move?
Because the object wants to stay still.
So the pencil was at, and it stays because, yeah. Your pencil was at rest, so it stays at rest because of its inertia. And this last one, this is true, by the way. I'm not making this up. Trains often use their brakes for an entire mile to slow down. This is why being on train tracks is so dangerous. If they see you a quarter mile away, they are going to be honking and all that stuff because they can't stop in time to not hit you. It takes like forever for a train to stop. That's why it's so dangerous to play on the train tracks. Even if they see you like a couple minutes ahead of time, a lot of times they can't stop in time. It's like, you got to get off, okay, because the train's going. Why does it take so long for a train to stop moving?
Because of its
Stay in motion.
It wants to stay in motion because of its inertia,
Its
but
mass is heavy. Speed.
big mass means
Big stop.
big
Big inertia.
inertia, okay?
Big
Objects with big mass have big inertia, and that means it's hard to change what they're doing. So a big object has big mass and big inertia, so that means if it's in motion, it is really hard to stop it. It also means if a big object is at rest and you try and get it to start moving, it's very difficult to do that. It's really hard to get trains to start moving, but once they start moving, it's really hard to stop them. Okay? If a train was going like half a mile per hour, you could barely tell if it's moving, and you got in front of it and you tried to stop it, it would be like there was nobody there, even if you were pushing as hard as you could, because the train's got huge mass, huge inertia, it would just run right over you anyways. Okay? Even if it's barely moving. All right. So that would be some possible test questions. But let's talk about some weight calculations. This we can kind of expect in your quiz on Tuesday. So here's our equation. Weight equals mass times gravity. What do I do if I want m by itself on both sides? What do I do?
Gotta divide it.
Divide by g. You guys are getting better at this, I can
This is
tell.
my favorite stuff.
G's cancel out, and there we go. So if you want to find an object's mass, you look at its weight, divide by the gravity experiences, which on Earth the gravity will be 9.8. You're somewhere else, you can't use that, but there you go. What if I wanted you to tell me what the gravity was instead?
You divide it by n,
Perfect.
so we can get the g by itself.
Correct.
So weight over mass equals
Correct. Absolutely. Alrighty. Well, let's use that to do little calculations. So mass will be weight over gravity. Gravity will be weight over mass. Alright. And where do we assume all these problems take place unless the question makes it clear? Thank you. Alright. What is the weight of a 0.15 kilogram baseball? Okay, what's the question mark? Okay, so then what's M?
0.15.
What's G then?
9.8.
9.8. Alright. And we got like 5 minutes. Make sure you're locked in doing these practice problems with us, okay?
Times 0.15 times 9.8.
Correct, Amunda. Weight equals mass times gravity. 0.15 times 9.8. What does your calculator spit out for us?
1.47.
Okay. I'll call it 1.5 for short. And that's a weight, so what are the units if it's a weight? No?
Weight over mass.
Look at your notes we just took. We said what the units were.
Oh, they're in the mid. Yeah, mine's
Weight is a force. What force is coming?
What's his Newtons?
Nailed it. Nailed it. Weight will always be in newtons. We measure weight in pounds as Americans. Quiet, please. We measure weight in pounds because we're Americans, but we're going to measure weight in newtons here in our physics portion of the class. Hey, what is the mass of a bowling ball that weighs 66.64 newtons? All right, so now we got the weight. We're looking for the M. What's the G we can use?
That's not funny.
9.8, because we're assuming it takes place on Earth. Okay, son. Okay.
That's your mom.
Emma. That we will be showing no one's mom. Mass equals weight divided by gravity. In this case, 66.64 divided by 9.8. What does your calculator spit out this time?
It is 6.9. Or I meant 8.
And what are the units if that's a mass?
G.
Kilograms. Kilograms.
That's the same thing.
Kilogram. Well, 1 kilogram is 1,000 times bigger than a gram.
Really?
Remember the masses we used in lab yesterday? Those are kilograms. A gram you would barely feel in your hands. All right, let's do 2 more real fast. Jupiter's acceleration due to gravity is about 25 meters per second squared. Okay? So that's Jupiter's gravity. How much would a 12 kilogram rock weigh? Well, we're looking for W again. We have a different G, so M times G. 12 times 25, what does that come out to be?
Do it in your head.
I did.
300.
300. 300 what if it's a weight?
Do it. Yes, Bray. Good job, Bray.
Yes, Bray.
Bray.
Good job. All right, here's the last one. It's a two-parter. What's the acceleration due to gravity on an unknown planet if a 91 kilogram man weighs 273 newtons? Do we have a W?
Yeah.
What is it?
273 years.
Do we have an M?
Yes.
What is
No.
No.
91 kilograms.
91. And we can't assume 9.8 because it's telling us to find the acceleration due to gravity, so we don't know what it is for sure. So that's what we're looking for.
It says no. It's over the same.
Gravity equals weight divided by mass. 273 over 91. What does that come out to be?
It is 3.
3 what?
Gram.
It's an acceleration due to gravity. Meters.
No, just meters per second.
Meters per
Second squared.
second squared. Second squared.
I can't.
All right, now here's my follow-up question. Think about this. All right, so we got 91 kilogram man. He weighs 273 on a different planet. Hold on, you want to stay with me for this last part. This will be great practice for you. What would this man's mass be on Earth? What would his mass be on Earth?
9.8.
That's the acceleration due to gravity.
3 times 9.8.
How would be
It'd be 270.
just to find the weight we have to do
9.8.
Hey, does mass change from planet to planet? No. So what's his mass gonna be?
90. Oh, no. Oh,
91. It's still just 91. Now he would weigh way more on Earth, but the mass, exact same thing. The mass on Earth and the moon is always gonna be the same. All about weight, okay? WMG. This is our equation right here. Weight, I don't know why that happened. Weight equals mass times gravity. Boom. All right, so what am I going to do to both sides if I want mass by itself? What do you do to both sides here? Divide by G. Absolutely. Because that will get G to cancel out over there. So, if you want to find the mass of an object, look at how much it weighs, divide by the gravity it experiences. What is this number usually going to be, by the way? The gravity? Huh? 9.8. Usually, if we're on Earth. If we're not, then you can't use 9.8. But a lot of times it'll be 9.8. Let's go back in time for a second. What if I didn't want to find the mass, but I wanted to find the gravity? What do you do to both sides of the equation now? Divide by m, right? So this may be the type of question where you're not sure if you're on Earth anymore. You want to find out what that gravity is. So what you do is you take the weight of the object, you divide it by the mass, how much stuff total are you talking about, and that tells you the gravity that object is experiencing. And that lets you know, oh, you're still on Earth, or you're not still on Earth. So anyways, you will have this equation circled in green. You will not have those two when you get to your quiz. And this will be at the top of your quiz on tomorrow, okay? But you just need to know when and how to use it. So I'm not going to tell you, oh, make sure you use 9.8 to this guy or something. Hey, CJ, let's do a quick. Oh, you're just kidding. I see. So let's do a couple problems here. We're going to skip the little warm-ups, 1 and 2. But let's go ahead and do questions 1 and 2 together. How about that? CJ, just need a pencil button. Okay. All right, it says, what is the weight of a 25-kilogram rock? Notice I got WMG, WMG, WMG down the side there. Yeah, you want to grab that little paper there? All right, so help me out. Let's see here. Jack, can you give me WM or G? Number or question mark is great. For the very first one. We skipped the warm-up of the first calculation. 25 is not for W. It says kilograms after it, so what do you think that might be? That's the mass. Yeah, that's the mass. Yeah, and that's why we're practicing. No big deal. The quiz isn't today, right? Hey, Wes, can you give me W or G? Number or question mark is great for this first calculation. Yeah, I need a number or a question mark for W or G. One of those. Yeah, sure is, because it says, what is the weight? All right. So then, Naki, I don't see any other numbers in the problem, but I need something for G. I need a number. What is that going to be? Yeah, because you can assume these problems take place on Earth unless the question makes it clear that it's not on Earth. So she's getting that from way up here. She's assuming Earth's gravity because the question doesn't say anything about there being a different planet or maybe even a different planet. So we assume, hey, we're talking about Earth here, 9.8. Great. That's awesome, Naki. So W equals mass times gravity. In this case, it's going to be 25 times 9.8. What does your calculator spit out, somebody? Yeah. And what should the units be? That's a weight, which is a force, by the way. Weight is a force. No, not quite. That's for masses and stuff, grams. What are forces in? Newtons, right? Weight is a force, how hard something's pushing on the ground or being pulled down by the ground. So you're going to put newtons on the end of that. We're used to saying pounds per weight, but it's in newtons when you're talking about forces, okay? All right, let's do one more together and let you guys work independently for a little while. What is the mass of a shelf that weighs 1,324 newtons? Connor, can you help me out? I need a W, an M, or G for the second calculation question. What is? Yeah. CJ, what were you saying? Oh, were you saying the same one? Okay. No, can you help me out? Can you give me M or G, number or question mark? It sure is. All right, then somebody help me. What's the G going to be then? 9.8. Again, we are assuming this happens where, Connor? On Earth, right? Here on Earth, right? Now, I'll tell you what, the next question you can't assume because I started talking about an astronaut and all that stuff. But, all right, so mass is equal to what we talked about earlier, weight divided by gravity. So in this case, 1324 divided by that 9.8. What does your calculator spit out this time?
I got it.
What you got?
I got,
Oh, you're plugging in. That's fine.
yeah, I got,
Plug her in.
I got 1,359.99.
That sounds like you might. I think you may have accidentally multiplied.
135.
Yeah, I think I'm looking at 135, like 1 or so.
5.1.
Yeah, there you go. Great.
I think I hit the times.
Yeah, easy to do.
I thought I clicked.
You're good. Easy mistake to make. That's why we always double check. What should the units be if this is a mass?
KGs.
kg, kilograms.
So if it says the weights in newtons, then it'd be kg always.
Mass is always going to be in kilograms. Weight will be in newtons. And gravity will be in meters per second squared because it's an acceleration. If you ever forget, like you can look at different problems. Like in number 1, if you forgot what weight was in, you can look right here like, oh, here's the weights given in newtons. Okay, so newtons for weight. All right, well, you guys go and get cooking. Number 3 is a great one. You're using that chart. Expect to see something like that in your quiz tomorrow. And I love 3A and B too. Those are really good. Good little thinkers. But go and get cooking. I'll drop off keys in a little bit once you guys have had some time to get ahead of me. Remember, this is like your quiz tomorrow, but it'll be long. This is longer than the quiz itself. Okay? Okay. Hey, so let's just do a little bit more of 3 because I think sometimes people overthink these guys, especially A and B. All right. So we're told about this astronaut. Her mass is 61.2, and she weighs 862.9 newtons. So we got to figure out where she is, which is really just an acceleration question, a gravity question, okay? So we find that gravity by taking her weight and dividing it by her mass. That's the acceleration she experiences. So what planet does she have to be on? Neptune, right? We're talking about Neptune for sure.
But why are you going pencils?
And a lot of you guys did really well on this. I saw 14.0s, 14.1s all over the place. That was great. Okay, make sure you put units on there, meters per second squared. If you ever forget that, they're actually in that little chart right there. But anywho, it says, what would the astronaut's mass be on Earth? How do you know? Mass. What would her mass be? Remember, mass is just how much stuff we're talking about total.
It doesn't change.
It'll be the J.
Doesn't change, right? So give me a number. What is her mass?
61.2.
61.2, right? So if you're asked a question like that on the quiz tomorrow, don't just say it will be the same. Like, actually give me a number. Because sometimes I'll see people be like, oh, it'll be the same. It'll be 862.9. Like, well, no, it's not going to weigh the same.
Well,
But her mass will be the same. Uh-huh. Yeah, so here's the thing. Mass. Mass is how much stuff we're talking about. It doesn't matter what planet she's on. She's still the same amount of stuff, like the number of atoms that make her up. So her mass, like, it doesn't matter if she's on the moon, Neptune, Earth, there, West. Her mass is 61.2 kilograms. That's not going to change anywhere. However, how heavy she is, how much she weighs, okay? Because you know how, like, on the moon you can jump way higher because gravity is lower and you don't weigh as much? So how much you weigh, that does change with gravity. I mean, think about the equation. W equals m times g. If you mess with g, let's say g gets bigger, then your W will have to change with it. Does that make sense? Okay. But anyways, so when I ask you what would her weight be on Earth, well, now we're looking for W. We know her mass is 61.2, and what's her gravity if she's on Earth? 9.8, right? So that does require a calculation in 3B, but 3A, I'm not trying to trick you in 3A, but a lot of people get goofed up there. They overthink it. The mass of something on 2 different planets can be exactly the same. Okay? It will weigh different. So weight is how much something's actually pushing down on the ground or being pulled down by the planet. Mass is just how much stuff are we talking about. Okay? If you're in space, outer space, and there's no gravity, okay, your mass is still 61 point, or her mass will still be 61.2, even though she doesn't weigh anything. Okay? So, anywho, does that kind of answer your question there, Wes? Okay, great. Well, I'll give you guys a couple more minutes here. I'll drop off the keys so you can do a couple, check a couple. And then we're going to move into some new stuff here shortly, okay? Here we go. So,